This is Grace, and today I'm going to tell you a romantic story about making prebiotic organics from Hadean crust via hypervelocity impact. This research is funded by NASA, Fundamental Laboratory Research Flare Work Package, and NSF. So do you know that in the first few hundreds million years after Earth's birth, from 4.1 to 3.8 billion years ago, meteors, comets, and asteroids of different sizes heavily bombarded on Earth's surface, a period of time commonly referred as putative late heavy bombardment. These impact events are often considered being destructive to life. At least we think dinosaurs are killed by impactors. However, re-examination of heavy bombardments yield different perspective. Exogenous impactors may not only have seeded sterile Earth with water and essential organics that originated in the outer space, but also have enabled synthesis of new organic materials as they penetrate through the primitive atmosphere, slammed into the ocean layer, and collide with the crust. Imagine a juvenile Earth without any organic materials. Carbon and nitrogen would have stayed as inorganic compounds and gotten recycled between atmosphere, ocean, crust, and mantle. Though the specific mechanism remained controversial, majority of the carbon and nitrogen in the mantle could have outgassed as carbon dioxide and nitrogen gas due to an early oxidation of the mantle, and therefore creating a carbon dioxide and nitrogen-dominated neutral atmosphere. The composition of the primitive crust is likely ultramafic, as suggested by remnants of komatiite that formed billion years ago. Interaction of CO2 with calcium and magnesium ions that dissolve from the ultramafic minerals can soon form secondary carbonates in the pore space and fracture zones, as suggested by the laboratory experiments and also the video showing you here. Extensive serpentinization can introduce nitrogen in the form of ammonia ions to substitute potassium in the clay minerals that present in the hydrous ultramafic rocks. This process could have been extremely efficient on early Earth, considering elevated volcanic outgassing rates and a more vigorous hydrothermal circulation driven by a higher surface heat flow. Consequently, a considerable amount of carbon and nitrogen could have been accumulated in the early Earth's crust, a hidden reservoir that have never been considered as a significant source of carbon and nitrogen to form prebiotic organics. In this study, we really want to know if we could synthesize prebiotic organics using inorganic carbon and nitrogen in the crust via hypervelocity impact. If we could, how much could we have synthesized? To answer these questions, we simulate hypervelocity impact plasma environment using high-power pulse laser ablation. We use Q-switch laser at 1064 nanometer under a minimum laser energy 70 millijoule and a pulse width of 9 nanoseconds. This laser enabled irradiance greater than gigawatts per centimeter square, sufficient to generate the thermodynamic plasma state of silica vapor generated by collision of two basaltic bodies. The laser system was steered and irradiated on the sample pellet. We performed all experiments at 10 to the minus 5 Pascal of the chamber pressure in order to mitigate the interference from ambient carbon dioxide and nitrogen gas. Ions formed in the plasma were then extracted and culminated by ion optics and sent to quadrupole mass spectrometer for detection. Each of our sample pellets contain a source of carbon, which is carbonate here, and a source of nitrogen from nitrogenous salt. They can either be sodium nitrate or ammonium chloride. Heavy labeled materials are also used. A quadrupole mass spectrometer measures the nominal mass of the ions and their intensity. Recombination of carbon and nitrogen that release from the both reactants allow the formation of cyanide ions, Cn, which has a nominal mass of 26. When the ablation target was prepared using a single isotopic labeled material, the mass of recombination ions will shift from 26 to 27. When both of the reactants are labeled, the mass station will shift to 28. This migration of the peaks as a function of the input materials reinforce that carbon and nitrogen atoms stand from the solid starting material in the plasma plume to form new species. Here are 4 mass spectra observed from the simulation experiments using calcium carbonate and ammonium chloride as starting materials. Each spectrum is a summation of 20 scans, and the y-axis is normalized to the total number of ions detected in each spectrum. The background of each spectrum has been identified using stepwise baseline regression and subtracted from the raw spectrum. In the label-free experiment, we observed the recombination of CN and CNO at mass 26 and 42, respectively. As we start to label a single reactant, we start to observe the peak shifted to mass 27 and 43. When both of the reactants were heavily labeled, we detect peaks at mass 28 and 44. We repeat similar experiments using calcium carbonate and sodium nitrate and observe comparable mass peaks at mass 26 and 42. The peak shifted with the application of isotopic doped reactants. We also observe NO2 as the decomposition product from nitrate salts. In the meantime, we realize accumulation of ions in the chamber that has been detected in the mass spectrum, such as chlorine in the nitrate experiment. Despite multiple sources of signals, both ammonium chloride and sodium nitrate experiments distinguish CN and CNO from other potential isobaric interfaces, providing confidence that the source of carbon and nitrogen are derived from the solid substrate. To provide complementary insights into the chemical and physical process associated with bombardments that may affect organic synthesis, we explored a second method to simulate hypervelocity impact environment. We used physical bombardment of carbon-60 bucketball on nitrogen-rich substrate. Heavy labeled carbon-13 bucketball was ionized, accelerated, and bombarded on an ammonium nitrate substrate at the velocity greater than 70 km per second. The ions generated were detected by a time-of-flight mass spectrometer. We observed isotopic labeled CN and CNO peaks at mass 27 and 43 respectively when heavy labeled carbon-13 60 bucketball bombarded on ammonium nitrate target. The isotopic labeled material are used. Then we observe migration of the peak to higher masses by 1 atomic mass unit. The significant peaks at the other mass station were observed during the experiment due to the presence of 20% carbon-12 contamination sourced from the projectile. The CN and CNO yielded at mass station 28 and 44 nonetheless represent recombination products from the labeled input material. We compared and contrasted the yield of CN and CNO between reduced nitrogen in ammonium and oxidized nitrogen in the nitrate form. The arrow bar represents 2 standard deviations of the yields from 4 experiments. The observation suggests that cyanide ions can be produced via hypervelocity impacts at a similar rate, irrespective of the redox states of the substrate. The twofold difference in yield of CNO suggests that reduced nitrogen in ammonium form is more efficient at generating CNO than oxidizing agent. With the both experiments, we have demonstrated the capability of synthesizing prebiotic organics via hypervelocity impacts using source of carbon and nitrogen from the crust. The next question is, how much prebiotic organics could we have synthesized? To address these questions, let's estimate the total reservoir size, the crustal reservoir size of carbon and nitrogen available for the organic synthesis. Spontaneous sequestration of carbon dioxide into the ultramafic oceanic crust and ejecta could have stored a significant amount of carbonate on the surface. The crust alone could have trapped 3 × 10⁻21 moles of carbon dioxide based on the box model of global carbon dioxide cycling through geological time. Abiotic fixation of nitrogen gas to nitrogenous salts is the rate-limiting steps and has to rely on energetic process such as lightning in the atmosphere or chemical reducing agents near hydrothermal vents. Assume an average 5 × 10⁻10 moles nitrogen gas is converted into nitrogenous salts per year. The crustal budget of nitrogen is estimated to be 10⁻19 moles. Assume all materials are distributed evenly on the Earth's surface. We could have a surface concentration of carbon and nitrogen as 10⁻13 or 10⁻10 moles per cubic kilometers, respectively. The mass of ejecta that shock to vaporize is on the orders of 6 times the mass of the incoming impactors that traveled at 20 km per second. Given the projected mass frequency of impactors during the late heavy bombardment, we calculate the mass of impactors that are above the threshold impactor size to penetrate an ocean layer and generate sufficient ejecta. The estimated total of 3 × 10⁸ cubic kilometer of crustal material could have been vaporized from the crust. If 0.1 mole% of the vaporized carbon and nitrogen recombined and condensed as organic, the continent and oceanic crust could have generated a total of 10⁻15 and 10⁻18 moles of organics during the 300 million years of heavy bombardment. This is equivalent to an organic production rate 10⁻7 to 10⁻10 moles per year, at least 4 orders of magnitude higher than the previous estimate of organic production rate via atmospheric shock in neutral condition. The story does not end here. After newly combined organics were rained down to the crater, they could have reacted with water and catalytic substrate near the crater basin to form molecular building blocks such as amino acids, nucleobases. Clay minerals formed due to the post-impact serpentinization plus wet-dry cycling could have promoted the absorption of a comprehensive panel of monomers and facilitate self-assembly of molecules. Interstitial pore space and fractures near the crater surface could have offered the optimal habitats to concentrate polymerized organic compounds and shielding them from harmful UV radiation and successive impact events on the surface. Because of these reasons, hypervelocity impacts could have been an invaluable mechanism to life's emergence on Earth. And this is Grace. I hope you enjoy my research, and let me know if there are more questions. Thank you.